Hey Calc friends, welcome to Chapter 5, Integrals. The first section in Chapter 5 talks about area in the sense of calculus. Our goal is to compute the area between a curve in the x-axis over an interval, a to b. So somewhere between a and b, our interest is to find this area that falls under the curve, but above the x-axis. Okay, so that's the area that we're looking for, this shaded area. All right, how are we going to do this? Well, the method is we're going to, if this isn't a nice shape like a straight line, either horizontal or on an angle, we have a curve, we can't calculate this area directly using geometry. So the idea is to use rectangles. We're going to split up the interval of interest into however many pieces we can. And we're going to allow those to be the sides of our rectangles. All right, but then what's going to be the height of our rectangle? We could go up the left side. We could use this rectangle to estimate that area. We could see in this case that would be a little bit of an overestimate. We could go up the left side and go across. We could use this area. Use that rectangle to estimate that area between those 2 points. That would be an underestimate. There's many different things we could do. We could actually go right up the middle of the rectangle, right here, and use that as the height to estimate the area between these 2 points right here. All right, so notice it's a little bit over, a little bit under. Maybe that will balance off. So we identify 3 different types of sums when we're estimating the area under a curve. The left sum is found as follows. We divide up the interval from A to B into however many, we call them approximating rectangles. So we'll do like 1, 2, 3, however many. We'll go all the way across. Right, and we're going to go to see where those points meet the curve. We'll do it all the way. So a left sum, literally, so we'll have however many little subintervals. Those would be the bases of our rectangle. So this would be the bottom of the first rectangle. This is the bottom of the second, bottom of the third, and this would be the bottom of the last. So to identify the height of the first rectangle, we go up the left side of the first rectangle. Where that meets the curve, that's going to determine the height of the first rectangle. So we would use this rectangle to estimate this area under the curve. So again, we can see in this case, it's a little bit of an over approximation. The second rectangle would go up the left side and would use the left side of the rectangle right there, and that would determine the height of the second rectangle. So this is the actual area under the curve. We can see the rectangle gives us just a little bit more. We go up the third rectangle, go up the left side where the left side meets the curve. That's going to be the height of the third rectangle. So that's pretty accurate in this case. That's almost the exact area. We're going to keep going on to the very last rectangle. We go up the left side where the left side meets the curve. That's going to determine the height of the last left rectangle in this area. And we're going to add up all those areas of those rectangles, however many we want. More is better. Right sum, on the other hand, we're going to take our interval from A to B. We're going to divide it into however many pieces. We'll keep going. All right, we're going to draw the sides of our rectangle at each of the endpoints of the interval, subintervals. Right here. Now a right sum, well, here's the bases of our rectangle again. So how many bases we have depends on how many pieces we break this up into. So this is my first base, my second base, my third base, all the way up to my last base of the last rectangle. This time, to determine the height of the first rectangle, here's the base. We're going to go up the first side where the first side meets the curve. That's going to determine the height of the first rectangle. So we go up the right side, but this is the base. So we're going to have to head over to the left like that. So here would be the first right rectangle and a right sum. So this time, this rectangle is a little bit of an underestimate. For the next one, here's the base of the second rectangle. We go up the right side of the second rectangle where that meets the function is going to be the height of the second rectangle. So we head over left. That's the second height. There we go. And then we continue this process until we exhaust all. So that would be the height. This would be my third right rectangle, right? And then my last one, we'll go up the right side, go over. And that's what we have. So that would be how we would find a right sum. Right, and then lastly, we have what we call a midpoint sum. We're trying to estimate the area under the curve f of x between x equals a and x equals b. We're going to divide it up into however many pieces we need. Again, more is better. We're going to go to where those sides meet the curve. Right now, to determine the height of the rectangle now, well, let's first look at, here's the base of our first rectangle, base of our second, base of our third, all the way over to the base of the last. So this is the first base. To determine the height of the first rectangle, we literally head up the middle of that given rectangle, that interval, the little subinterval, we head up the middle. Where that hits the curve, that's going to be the height of the first rectangle. So the height of the first rectangle is determined by where the midpoint of this interval hits the curve. And this rectangle would approximate that little bit of area under the curve between these 2 points. Base of the second would be this guy. I'm going to go right in the middle. We're going to head up right here where the middle x value hits the curve. That would be the height of the next rectangle. And this is kind of nice because we have a little bit of an underestimate here and a little bit of an overestimate here. So midpoint sum tends to work out really nice. Okay, for the third base, we're going to head up the middle. Where the middle meets, that's going to determine the third height of the third rectangle. And then we're going to continue this process until we do this for every rectangle. Here's the base, head up the middle, where the middle meets the curve. So this one's going to be a little over on the left and a little under on the right. So that would be my rectangle. And then we would calculate these areas because we can find the areas of rectangles quite simply. So let's try this with an actual example. All right, let's look at the parabola y equals x squared. And I want to estimate the area. So here's 1, here's 5, right? I'm going to estimate the area under this curve between 1 and 5. So here's my curve. Now there's no nice geometric formula for the area of this shape. If it was a triangle or a square or even a part of a circle, we could use geometry. But we don't have that advantage here because there is no template for the area created by a parabola. So it says to use 4 rectangles. So I'm going to divide this up into 4 pieces. So if I divide it up into 4 pieces, and I conveniently used 4 because we went from 1 to 5. So if we divide 1 to 5 into 4 pieces, would go from 1 to 2, 2 to 3, 3 to 4, and 4 to 5. And we're going to go up where these guys meet the curve right there. Now we're going to have to create our rectangles. So a left sum. So the left sum for this problem, so it's telling me what sum to use. It says go up the left side. Where the left side meets the curve, that's going to determine the height of this rectangle right here. So this is going to be my first rectangle. Well, where does 1 meet the curve? Well, remember, it's on the curve y equals x squared. So if x is 1, the height is going to be 1. So the width is 1. This right here has a width of 1, and in this case it has a height of 1. So that little green rectangle, the area is just a 1 times 1. Right. And then the second one, we're going to go from 2 to 3. It's a left sum, so we're going to go up the left side. Where the left side meets the curve, that's going to determine the height of the second rectangle. Well, the left side was going up above the 2, so 2 meets the curve x squared at the y value 4. So now we have a base of 1 times a height of 4. We're going to continue with this process. We go over 1, we go up the left side. The left side meets the curve right here. If we follow 3 all the way up, it goes to a height of 9 because it's on the function x squared. So it's going to be 1 times 9 plus, oops, let's draw that one in. And then we're going to have a base of 1. We go up the left side. It's going to go up to 16 because we went up the side where x equals 4. 4 squared is 16. That's going to be 1 plus 16, which equals 30. So we can see that's an approximation. It's an underestimate because the curve is increasing, and when we have an increasing curve and we use left sums, the height of the rectangles are always going to fall below the curve. We can say it's about 30. All right, let's try this again, but use a right sum. See if we can get a different estimate. So here's the curve, y equals x squared. We're going to go between 1 and 5. Right, and I said n equals 4, so that's a little subscript. We use r with a little subscript of 4, indicating that we're breaking it up into 4 pieces. So 2, 3, 4, and 5. So these will be the base, my 4 bases, and each will have, we're going to say, I'm going to use the notation here, we're going to say delta x is equal to 1. What we did is we took the width of this interval, which is 5 minus 1, and divided it by how many rectangles we have. We get 4 over 4. That one was just easy to do in our head. We could just see it visually. All right, so now I'm going to draw my lines of each of the endpoints of my subintervals. Now when I do right sums, be careful here, because here's the base of my first rectangle. I'm going to go up the right side of the base where that reaches the curve, which is at 4. Now my first rectangle, here's the base and here's the height, which is determined by the right side of the rectangle. So in order to create this rectangle, I go from this point and I head over left and go down. So now this rectangle, my right sum, falls above the curve. So our 4 is going to be, well, my base is 1 and my height is 4, plus I'm going to go up the right side where the right side meets the curve, which is 9. That's going to determine the height of the rectangle. So it's going to be 1 times 9, plus my third base is also 1. I go up the right side. So even though I go up the right side to form the top of the rectangle, I have to head over to the left, right there, and that reaches a height of 16. So this is a 1 by 16 rectangle. So that rectangle is going to contribute an area of 1 times 16. And then my last one, this time, go all the way up to 5. I'm going to be at 25. The height of this rectangle is 25. This is going to be 1 times 25. Okay. And we add that all up and we get 54. So therefore, we can conclude that the actual area between f of x equals x squared and the x-axis is somewhere between 54 units squared and 30 units squared. 30 came from our left sum, 54 came from our right. We can see that 54 is too much and that 30 is not enough, so it's somewhere between 30 and 54. Right, we can get a better approximation by doing more rectangles. Or we can use what we call the midpoint sum. So let's just practice a midpoint sum before we try to do this with more rectangles. So we're going to go from 1 to 5. We have y equals x squared. All right, so this is where it gets a little more complicated. 2, 3, 4. So we're still going to go up. And have our 4 subdivisions. So 4 subdivisions leads into 5 endpoints. We have the leftmost endpoint, 3 in the middle, and the rightmost endpoint. So 4 subdivisions lands up with 5 endpoints, right? The width of each delta x is equal to 1. That's how the width of each base. Now how we determine the height varies. In this case, we're going to use the midpoint sum. So we're literally going to go halfway in between, right here. Right in between 1 and 2 is 1.5. And where 1.5 meets the curve, that's going to determine the height of that first rectangle. So we're going to go across, and this first rectangle is going to be, well, the midpoint sum. It's going to be the base. Well, how high is this rectangle? Well, it's where 1.5 meets the curve. So instead of taking out my calculator now, I'm just going to do 1.5 squared, because whatever value this is, it's 1.5 squared. Would get the output just by putting 1.5 into the function y equals x squared. We're going to continue with this for my second rectangle. The base is still 1, but the height is going to be determined by the midpoint of that second interval, which is between 2 and 3, which is 2.5. So I'm going to go up to where 2.5 meets the curve. 2.5 squared is going to be the output. 2.5 squared plus 1 times, well, let's do this. This is the height of that rectangle. And then the midpoint of the third rectangle is 3.5. So the base is still 1. The height is going to be where 3.5 meets the curve. Okay, so I'm going to do this. So 3.5 squared. I ran out of room, so I'll just put it down here, plus 1. And then the midpoint of the fourth subdivision is 4.5. 4.5 meets the curve way up here, right? So whatever 4.5 squared is would be the height of the very last rectangle. So we really can't tell if this is an overestimate or an underestimate. It's a little bit of both. So each rectangle goes over the side of the curve and it's under the curve a little bit. So maybe those will balance out. And if you calculate this, you get 41. So that actual area is approximately 41. We're not guaranteed it's exactly 41, but it's just another way to estimate the area under the curves. All right, let's see what happens if we use 8 rectangles instead of 4. So I'm just gonna do, let's do a left sum. We're gonna do left sub 8. So left sub 8, we're gonna go to 1 to 5. We're gonna divide this up into 8 pieces. So we're going to, my delta x, the width of each interval is going to be 5 minus 1, which is the width of the entire interval. We're gonna divide it by 8. So that's 4 over 8, which is 1/2. So each of my rectangles is going to have width 1/2. So I'm gonna go from 1 to 1.5 to 2 to 2.5 to 3, 3.5 to 4, 4.5 to 5. Now notice, as I draw my rectangles, they're gonna be a lot thinner this time. They're gonna be half of the width of the previous one. You can do whatever the problem calls for, left sums, right sums. In practice, we would do as many rectangles as possible. So if I do a left sum, I'm gonna go, so each of these has width 1/2. I'm only gonna write it in once. If I go up the left side, where the left side meets the curve is 1, and I'm gonna go across, that's gonna be the height of my first rectangle. So it's gonna be 1/2 is the base of the first rectangle, and the height is 1. I'm gonna put 1 squared just so we can see the pattern here, because to get the output at 1, we put 1 into the function y equals x squared. All right, now we're gonna go up the left side of the second tick mark here, and this is 1.5. So we go up the left side, we see where that meets the curve, and that's gonna be the height of my second rectangle. So the output here is 1.5 squared. So the base of the second rectangle is 1/2. The height is 1.5 squared. Plus, and we're gonna continue on this process. The third endpoint is 2. I'm gonna go up where 2 meets the curve. That's going to be 1/2 times 2 squared plus 1/2. This is 2.5. All right, 2.5 squared. It doesn't, that should really be in there, but that's right. Same thing. 1/2. We're going to go up the left side. Where the left side meets the curve is where 3 hits the curve. So that's going to be a 1/2 by 9, or 3 squared. I don't know why I'm alternating. I had no reason. Just not really paying attention as much as I should. So then we're going to go up 3.5. We're going to go up the left side. Where the left side meets the curve is 3.5 squared. So the area of the 6th rectangle is going to be 1/2 times 3.5 squared. And then this rectangle here is my base with 1/2. I go up the side of 4, where 4 meets the curve is going to be 16, because that's 4 squared. So it's going to be 1/2 times 4 squared. Plus, we're so close. We got 4.5 right here, and that's my last one. All right, we're going to go up the left side where 4.5 meets the curve. Now, if we look at this and compare it to the area that we obtained from L4, that is the left sum using 4 subdivisions, just logically, we can see that there's definitely, it's a closer estimate. This is the area that we missed when we only used 4 rectangles. We don't have nearly as much missed area, so we expect L8 to give us a better sum. Unfortunately, I didn't do this ahead of time, so you're just gonna have to bear with me for 1 second. Let's pop this in the calculator. All right, 2.5 squared plus 1/2 times 3 squared plus 1/2 times 3.5 squared plus 1/2 times 4 squared plus 1/2 times 4.5 squared. Let's see if I got them. 1, 2, 3, 4, 5, 6, 7, 8. Looks like I got them, right? So this is equal to 35.5 units squared. Now notice we don't know what the units are, so we tend to just leave them out when we're talking about area under the curve unless we know the units. So if I go back to this approximation, I can now conclude that it's between 35.5 and 54. And we can bring this in a little bit by doing more rectangles. We could do R8. Even better, we could do R16. We could do R100. The more rectangles you do, the better estimate you'll get. So what is the best estimate? What would N have to be in order to create the best estimate? Well, you'd want that base to be as small as possible. You would want to take as many rectangles as possible. So in theory, we would take infinitely many rectangles. We would look at these sums as N goes to infinity. So the area of the region of a curve that lies between the curve f of x and the x-axis over the interval is, the limit of the sums of the approximating rectangles as N approaches infinity. So we're going to go from A to B. This area, we're just going to divide it up into as many rectangles as possible, like that. And we're going to use these rectangles to approximate the sums. And as N goes to infinity, it doesn't matter if you use right sums, left sums, midpoint sums. We're even going to learn about different types of sums in Calc 2. So we're looking for this area. So this entire area from here to here is the limit of the sums of the approximating rectangles. So the notation is a lot more horrible than the process. If you understand the process, that's fine. Don't get too razzled about the notation. But let's write it up. So we're going to say, let my first endpoint be, we call it x sub 0. We're going to call that A. And we're going to call my last endpoint, so this is going to be x sub 0. And my last endpoint is going to be x sub n. Right, so if we have 4 rectangles, we're going to have 5 endpoints, because this would be the first one would be the 0th one, the x1 would be the second, x2 would be the third, so that would go all the way up, right? Then the width of each rectangle is the length of the interval, b minus a, divided by how many rectangles you have. All right, so like if we looked at a number line, this would be x sub 0, the next one would be x sub 1, this would be x sub 2, would continue all the way. This would be x sub n, the one before this would be the n minus 1. So if this was the 4th one, that would be the 3rd one. And then the notation we use is, I said don't get too riled up about this. Let's see, let me pull that down, okay. So the left sum is, well, we go up the left side, so we're going to start here at x sub 0, and we hit every left side. This one wouldn't count, so in our last rectangle, this would be the side we'd go up. So it's delta x times the height at the leftmost endpoint, plus delta x, which is the width of the rectangle, times the height at the first endpoint, plus delta x times the height at the 3rd endpoint, which would be f of x2. We continue this all the way up to delta x, which is the last one, and then we go up the left side, so it'd be the function evaluated at the next to the last endpoint of the interval. And then we typically write this in sigma notation. In math, this Greek letter sigma means sum. We see delta x, and we see f of x, but x, the subscript on x changes, so we write that generically with an I. My i's start at 0 and the end at n minus 1. So that's the notation we would use to represent the left sum? Well, the notation we would use to represent the right sum would be, well, we're going to go up, on my first interval, we're going to go up the right side. So it's going to be, the base is delta x, and then we're going to go f of x sub 1. So we don't use x sub 0 in the right sum. We don't use x sub n in the left sum, plus delta x, f of x sub 2, plus delta x. The height would be f of x sub 3. And we go all the way to the very rightmost endpoint. This time we hit the very most right endpoint. Now notice the only difference between the left and the right sum, they all have the middle terms in it. The left sum has delta x times the output at the leftmost endpoint, where the right sum doesn't. But the right sum has the width times the output at the rightmost endpoint. That's not in there. So if we eliminate those two, the sum, that part of the sum is exactly the same. Right? And how do we condense this? Well, we use the sigma notation. Sigma means sum in math. We have delta x, and then we have f of x, but what's changing is the subscript, so we call that I, and here I starts at 1 and ends at n. So that just means that. The notation for the midpoint is a little bit hairier because it's a little more ambiguous. The midpoint sum, right? So in this case, we would take the point in between here. We would take the point in between here. We would take the point in between here. So how we write that is we say delta x, f of x star 1, plus delta x, f of x star 2, because it's not x1, it's not x2. This point is in between x0 and x1. This point's in between x1 and x2, plus delta x, f of x star sub 3, plus all the way up to delta x, f of xn with a star, right? The notation is, we have delta x, we have f of x star, where the subscript is changing, and the subscript changes from 1 to n. And then what does the f star mean? F of x star? Well, this means the midpoint of the first interval. This is the midpoint of the second interval. This is the midpoint of the third interval. So let's just write down there where xi star is the midpoint of the interval of x, the one before it and the one with that value. So f of x star sub 2 would be, this would be the midpoint of the interval between x1 and x2. So one before it and at that point. This would be between x2 and x3. This would be between xn minus 1 and xn. Right, so how do we find the actual area? Well, we would do this, but we would let n go to infinity. And if we let n go to infinity, this sum is going to equal this sum, which is going to equal that sum. So your goal is to take as many rectangles as possible. So the actual area between f of x and the x-axis over the interval ab is equal to the limit as n goes to infinity of the sum formed by left rectangles, which will be the same as the limit as n goes to infinity of the sum formed by the right rectangles, which will be the same as the limit as n goes to infinity of the sum formed by the midpoint rectangles. All right, so this is very geometric. Don't let this trip you up. It's just finding the area of rectangles. If you have any troubles, be sure to zoom in. Good luck.